So hello everyone. Today we are here with a new problem of lead code, that is lowest common ancestor of a binary search tree. So before moving toward the problem and toward the solution, it is better to understand that what is binary tree and what will be our approach to solve this problem. So let's see. Suppose this is our binary tree, and so first let's see that how we will going to create this binary tree. So we have given some numbers like this. So what happened that the first number of any series, like we have given it in the form of array or anything else. So the first number is our root node that I have made. Okay. And now the binary tree have the special condition that for any parent node, the left child means its left child is always less than its parent node. Okay. And its right child is always greater than itself. Like we can see over here that first we have given the 10. Okay. We made it as a root node. Then we got 5. So 5 is less than 10. So we put it toward its left. Then we get 2. So now then 5 is less than it. So we put it toward its. Okay, someone is else in the meeting. So 5 toward its left and 2 is left to it is 5. So we can see over here that 5 is less than 10 and 2 is less than 5. Now we got 7. So the second condition of binary search tree is that the right child, is always greater than its parent node. So here we can see that as we get 7 here, so where we put here. So 7 is less than 10 means it is on the left side, and 7 is greater than 5. So that's why it came toward the right side of this 5. After that we got 15. So 15 is greater than 10. That's why it will be put toward the right of it. And then we got 12. So 12 is greater than 10, but it is less than 15. That's why it goes left to this 15. And then finally 20. So 20 is greater than 15, and we came up with this rightmost of the tree. So here, like this way we can see that the minimum of binary search tree is always toward its leftmost side, and its maximum is always toward its rightmost side. So now we are clear up with this that what is binary search tree and how we will create the binary search tree. Okay, now we came up with the problem. So let's see what is the problem now. Given the binary search tree, that is BST, find the lowest common ancestor LCA node of two given nodes in a BST. According to the definition of LCA, Wikipedia, okay, we don't have to watch it. The lowest common ancestor is defined between two nodes P and Q as the lowest node T that has both P and Q as descent. So this is the basic definition that what is the lowest common ancestor. So we came here with our, so let's see how we're going to approach this problem. So suppose we have given 2 and 7. So the lowest common ancestor of 2 and 7 is 5, because 5 is the only one which is very close to this. So 2 and 7. So the answer will be 5. Suppose we got 12 and 20. So the answer will be 15. And suppose P and Q will be 5 and 15. So the answer is this 10. So now how we're going to approach this question? So basically we have given two conditions that we know that the left side is always greater than is always less than this parent node, and the right child is always greater than this parent node. Okay, so what we do, suppose, so we got the condition that for anything, like we will check that if these two values like P and Q is less than the current. Suppose let's take an example that we want to check this for P equals to P equals to 2 and take 7 as Q. Sorry, it's look like 9. Now it's look like Q. Now we know that we always start our traversing from this root node. So currently the pointer is at this root node, means at this 10. We are here. So we will check that if P and Q is less than this 10 or vice versa of this, that if this 10 is greater than P and Q. So in both the condition, we know that the answer is on our left side. Means if the current position at which we are is more than P and Q, so this means that we are on the higher side. So we have to go on left side, because as per our the condition of binary search tree, the left side is always smaller than the parent. So we came here. Now at this position again we check if P and Q is less than sorry, if P and Q less than this parent node. So we can see that 2 is less than 5. Okay, the condition is true, but this 7 is not less than 5. So condition is false. Now again we check the second condition, that is this current node, means now we are on 5. Is this current node greater than P and Q? Okay, let's see. 5 is not greater than 7. So at this point, we know that this is our answer, because one side is less than this current node and other side is greater than. So this means that this is the parent node and this is only the lowest common ancestor. Now take another example. Suppose we got 12 and 20. So again, we will check. So the as per our first condition, we start traversing from this 10. Okay. Now we will check that is this 10 greater than P and Q, or vice versa of this, is P and Q. Now P is 12 and Q is, let's make it look like 0. So, okay. Is P and Q less than this 10? No, it is greater than this. So what we will do now, at this situation, we know that the answer is on the right side. So if it left side condition gets false, so we move toward this right side. Now the pointer came over here on this 15. Now on this 15, again we check that is 15 greater than both P and Q. Okay, let's see that. So 15 is greater than P. That means 15 is greater than 12. Condition gets true. But in that we use AND condition. So 20 is not less than 15. So at this point, the condition gets false. And as soon as this condition gets false, means it's proved that we are at that point where this 15 is the parent node, because the left side of this node is less than this, and the right side is greater than this. And also, so because we check both the conditions, the the right side condition also, the left side condition also, means this is our answer and we will return this. Now how we will going to implement this in our code? Let's see this. So we came over here. Now one thing we have to look at this point. Let's go further and then I'll make a reminder of that. So first we have to start traversing. Now we don't know over here that up to what extent we have to go. So I'm going to solve this problem using recursion also and using using loop also. So in Python, I will do it using loop. So I just write while. So in this, we don't know that at which extent we have to go. So I just write like while root, sorry, root means until it is true. So at this point now I will check that. So as per our first condition that we have to check from the left side. So I write if root dot val, or I can write vice versa of this. So no problem. If root dot val is greater than p dot val. Now why I have written p dot val over here? We have to see this. So as in this function signature, we can see that, focus on this. We can see this root is of tree node type, means it is pointing to the this root node currently. And p, it is also a tree node type. That's why it is not a like a single variable. That's why I have written over here p dot val. So and root dot val greater than q dot val, means the point at which we are currently, suppose we are at this 10, it is greater than both p and q, like 2 and 7. So this means we have to go on left side, or we can write vice versa of this, that if p dot val is less than q dot val, so we can write like this. We also, okay, I will write at the end, no problem. So at this point we have to go on left side. So what I will do, I will write root equals to root dot left. Now the second condition, if suppose both the values are greater than the root values, means at point which we are pointing, so it is less than both the given values. So elif, I will write elif root dot val is less than p dot val and root dot, sorry, I have written care, root dot val is less than q dot val. So means currently we are pointing to a node and it is less than both the values. It is less than both the given values. This means that both the values are greater than this current node. So this means we have to move on right side. So what we have written, root equals to root dot right. Now finally, if suppose these both the conditions get false, so it happens at which point? So it happens at that point where, like suppose for this 2 and 7, it happens at that point where this parent node, means where the node at which we are pointing, its left side is less than this node and its right side is greater than this. So at this point, both the condition gets false, because here in both the conditions we are using and. So they will get true only when they both the in if they both the conditions get returns true, then only it gets completely true. And in any case, one returns false, then then it gets false. So finally, if suppose the both the condition gets false, means we are at the node where we get our answer. So at final, else, break, sorry, break. We just break the loop and we came out, and finally we return root, because now at that point where this condition get these two condition gets false and we break the loop, we came out. So now we are at that position where we got our answer. So I hope it is clear to all. So now I'm running it. That so it is running, and it, yes, the solution is correct. So maybe for this is one of the efficient approach, and now it is running on it is running on 156 microseconds. You can see that it is also running it for 40 microseconds and 78. So it's not matter a lot. So as I told you that in the if condition we can just write vice versa of this, it will not affect much. Like if I have written that if p dot val is less than loop dot val. So we have written that only that if here we have written that if root dot val is greater than q dot val, and here we have written p dot p dot val is less than root dot val. So the both the things are same and both are correct. So as I told you that we are going to do this problem from different languages. So just now we did it using Python, and now we will solve it using C++. So I have already written this code in C++ because the logic is fully same. So here we have used in Python we have used the looping, and here we have used the recursion. So let us understand the logic. So in recursion, we know that there is one base condition is always there. So the base condition is until null. So the root, if root equals to null, then what we will return? We simply return null. And second, if now the same condition that we did in Python, the first one is that only that if p dot val is less than, let's just reverse it so that it won't create. Okay, okay, it get okay. Let's see this. Mm, sorry for the technical issue. So we can see the condition as same over here also, that if root of val is greater than p of val, and Root of val is greater than q dot val. Same that we did in Python. Here is also same thing. That if we are at the point where the node is greater than both p and q, so this means we have to move on left side. So in recursion, what we call the lowest common ancestor, that is the same method. We call that same method, and what we return over here, root dot left. Sorry, or we can say root of left. So means we are going toward the left tree. As per the problem, we can see here with this example. So suppose we want to search for this 0 and 4. So currently we are on 6. So we check that it is not null. Then we saw that root of val is greater than p of val. That's yes, both are true. Both condition gets true. So we came in this, and we in recursion we return this root of left. Means now we are focusing on this 2, and same p and q. P and q is always same because we are comparing with them. And suppose if we search for 7 and 9, then this condition gets false and this condition gets true. So in recursion, we call this. And if suppose at any point these two condition gets false, these both the condition gets false, then what we did? We just return the root. We simply return that point where we are currently. So I hope that this question is clear to you, everyone, and thank you for watching. That's all for today. In next session, we came up with another problem of DSA. Thank you.